So we're going to take a look at the solutions to the Unit 2 test, courtesy of many of your classmates over the 4 periods we have. Let's get started. So we're looking at the knowledge and understanding section, the first 3 multiple choice questions. The first one was to find the minimum value of a function given in, vertex form. So that's quite simple. I mean, if you notice that, the vertex is at 4 and -2, so it's over here, kind of opens up. And again, I'm using these values, the h and the k. The minimum value will be -2, or b. For part 2, it asks for what value of k makes the equation true. All you have to do is really just multiply out what is on the right-hand side. So just kind of bring these over, multiply them using the distributive property, and you end up with x squared minus 5x and plus 6. So my k value is going to be 6, which is the answer is A. The last part, number 3, you had to find the vertex of the equation given in the x value of the vertex of the equation given in factored form. And there you just had to kind of, read off the roots and find their midpoint, so -8 and +2. Divide by 2 to give us -3. So the answer was -3. Moving on. So here we're looking at question number 4. We're trying to solve by factoring. The solution is courtesy of Sierra Knapton. And let's take a look at what she did. So I'm going to just get maybe a white pencil, which you can see on the surface. As you can see, she brought all the terms on the right-hand side over to the left, collected like terms, and what she ends up with is a quadratic and equaling 0. She then realizes, okay, well, I could probably factor what's on the left-hand side. So over here you see, her factoring, 2 numbers that add to give you -1, multiply to give you -30. Those numbers are 5 and -6. Again, the technique I used in my class at least was to divide those numbers by the leading coefficient, which is 2, and the fractions kind of, they give you the factors of your quadratic. So you'll notice here, this 5 over 2 is going to be the 2x plus 5, and the -6 over 2 or -3 over 1 is going to give you this factor here. Now, one observation I noticed when marking a lot of these tests was that, some of you stopped at this stage, right? You stopped right here. And remember, the question asked, solve. Solve means to find the roots. So it wasn't enough to factor. You actually had to get the values of the roots. And, because in this case, your fraction, -5 over 2, works out as a decimal that's terminating, that was acceptable. Infinite decimals, we prefer you leave them in simplified form, not actually valuing the decimal unless it needs to be. And we'll see that in question number 5. So question number 5, we are solving an equation using the quadratic formula, and the answers must be fully simplified. Again, that was in italics. So, there were cases where people did not do that and maybe might have lost half markers or so, especially at the end. So let's take a look at this solution courtesy of Mateo. He starts by, just like the previous question, bringing everything over to the left-hand side. So, all this stuff over here, just, tosses it over to the other side and simplifies, collects like terms, and thereby identifying his A value, his B value, and his C value, which he then plugs into the quadratic formula over here, does all the calculation, and ends up with 10 plus or minus square root of 296 over 14. At this stage, he factors, or kind of breaks down the the radicand here, the 296. So 296 to 296 happens to be equal to 4 times 30, not 37, that's what he had before. 4 times 74. Okay. And the reason why, we're identifying it as 4 times 74 as its, factorization is because 4 is a perfect square, which you can then break down. Okay. This step here, not really so important. And, there's a few things going on over here in this step, but I'll explain. So 296, okay, as a square root is the square root of 4 times 74, which is also going to be equal to the square root of 4, square root of 74, which is equal to the 2 times root 74, and that kind of brings us over here. Okay, what he did, Mateo, was he actually factored out the 2 from the two terms, the 10 and the 2 root 74. So this guy actually is what's this 2 out here. Kind of identify where he can simplify, namely this 14 and 2. They drop down by a factor of 2, so this will become 1, and the 14 becomes 7. And here's where he gets his final answer of 5 plus or minus root 74 over 7. And, kind of breaking that up with the plus and the minus, he has root x1 and root x2. Now, some of you, went on and put this into decimal form. Fully simplified means that, okay? Fully simplified means, don't put it in decimal form. Leave it as a radical. Again, this isn't a word problem, so, as exact as possible as we can get with a solution, that's what you want to write as your final answer. In question number 6, we wanted to use the discriminant to determine the number of x-intercepts in this equation here. And if you recall, the discriminant is negative b. That should be in brackets. It's actually not negative b, it's positive b. But whatever, negative b squared is going to be the same as positive b squared minus 4ac. So this solution, again, courtesy of Joseph Mongillo, he took the a, b, and c values, as you can see over here, and just tossed them into the discriminant formula. Now, obviously, he made a mistake here in the way he stated it, but the end result is the same. So I'll just put a negative 8 over there. And you'll notice that after all the calculation is done, you get it equal to 0. Now, his work is good. I probably wouldn't, say, okay, equal to 0, equal to 0, equal to 0 until the very end. I mean, you're trying to determine whether or not the discriminant is equal to 0, because if it is, then you have one x-intercept. So, not ideal to do this necessarily, except at the very end to actually show that the discriminant is equal to 0. But once you get to that conclusion, there is one real root. Here in question 7, we're looking at a quadratic linear system of equations. We want to find where they intersect. This solution, courtesy of Cailey Freeze, I'll kind of walk you through it. So whatever this quadratic looks like, I know it's opening up something like that, and then I have some kind of straight line. Now, does that line intersect the quadratic? Well, it could over here, or maybe it can touch at one point, or maybe it doesn't at all. Okay, we really don't know. Okay, but we'll see. We'll see what we get. So what does Cailey do in this question? Well, first of all, she's like, okay, well, if they do intersect, then at some value for x, or values, they have to be equal to each other. So that's step number 1, is actually equating the two equations to each other, and collecting everything over to the left hand side. Again, seems to be a recurring theme of this unit, and setting it equal to 0. Now the reason for that is because, well, we have a quadratic over here equal to 0. I guess how do we solve for that? if you can't, do a factoring technique, just, apply the quadratic formula. So that's what she does here, identifying her A, B, and C values. Again, careful. It's -8 squared. If you just had -8 squared without the brackets, it would be -64, which is not the case, right? It is +64. But, she puts in all the values A, B, and C in the right place, does the work, yada, 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 through here, and ends up with 2 values for x, which means there are 2 points of intersection. One is at 2, and the other one is at 2/3. Now, again, I noticed some students ended there and just thought that was it. But it does ask for the points of intersection, and a point consists of 2 coordinates, an x and a y. So these are the x values. You can think of this as x1, this is x2. If you want to label it, you still need to find the y values, and to do that you can plug either of those two into the original 2 equations. Now if I had to choose between the quadratic and the linear, as Cailey did by the way, I would choose the easier of the 2. So the linear equation is a lot simpler to calculate with. So by plugging in the x values into there, we get our y values of -12 for 2 and -5.33, repeating really, for x2, for the 2/3. Again, try to get into the habit, unless it's a word problem, to leave your answers as a fraction. So this would be -10/3 minus 2, let me get this out of here, over 1, which becomes -10/3 minus, what is that, 6/3, -16/3. Okay, so 5.3 is -16/3. So 6/3. And again, she forgot the negative there, but it's still good. Okay, so that is a solution to a linear quadratic system. Okay, we're going to take a look at the first thinking question of the test, probably one of the hardest questions on this test. Let's check it out. So we have a rectangular area. It measures 20 by 50, and it is extended by a uniform width on just one of both the longer and shorter sides. So this extension adds an extra 900 square meters to the rectangle. Now we want to find the dimensions of the new rectangle and make sure we have some kind of visual on that as well. So let's look at this solution, courtesy of Alexia Himelfarb. Very well done. Beginning with, let's look at the actual diagram. So it was a rectangular shape. So that's what she kind of drew over here. Okay, she has this rectangular shape, and the uniform width, okay, is being added on each side. Okay, so here she extends by a uniform amount to the 50 meter side, and also to the other side, okay, the 20 meter side. Okay, she extends by a uniform amount, and this goes to the edge like that. So because this is a uniform width, uniform meaning the same, it's going to be that far on this side and that far on this side. So how did she come up with an expression for this new, this new area, right? Because what she's doing is she's adding on to here, all of this that I'm, scribbling out. That's 900 square meters. 900 square meters. So what does she do? Okay, well, this side is 50. If I add on an x, it's going to be 50 plus x, right? And same over here. If this is 20 and I add on an x, this whole thing is going to be 20 plus x. Okay, looks good. We have a length and a width, for the larger shape. And the original area, by the way, is just 20 by 50, or 1,000 square meters. So what does that mean the whole area is? Well, it's just the sum of its parts, or 1000 plus 900, or 1900. And in particular, right, let me go over here, because this is where the expression is. In particular, okay, I can now create an expression for that new area. Okay, I have 1900 on my left side, and the dimensions, of the extended rectangle on the other, and they must be equal. Okay, so expanding everything, collecting like terms, I end up with a quadratic, and quadratic equal to 1900, right, equal to 0 once you bring everything over to the left or right hand side. Well, you're just using the quadratic formula, which is what Alexia does all through here. I'm not going to go through the details of that. I think you can calculate it for yourself, but you'll notice that she ends up with two answers, one positive and one negative. The negative she discards because, you can't have a negative lengths, at least not in this world, this universe. So once she figures out that x value, or the uniform width, the uniform length that's extended on all sides, she can then answer the original question, which was, what are the dimensions of the new rectangle? Okay, so the new rectangle is just whatever the original ones were, plus the 11.1, and that's what she has over here. So your final dimensions are 61 and 31.1, which is, as a concluding statement, this over here. So I think the hardest part, probably where people struggled the most, was getting this visual, okay, this diagram. But once you got that and you were able to set up your formula, the rest, okay, is pretty mechanical. Okay, this was the thinking part, really setting up the diagram and establishing an equation based on that. Let's move on. So in this next question, we are trying to determine an equation in standard form for a quadratic function passing through the point 4, -2. Just highlight that uniformly, and with a vertex of 210. So this solution here brought to you by Ottey. Let's take a look at what she does. So she begins by, writing the vertex form of the equation with the values of the vertex, the h and k, one over here and one over here. Again, just taken from the wording of the problem, and puts it directly in. Now, that's not enough because we don't know how this parabola opens. Does it open up, down? Is it a minimum, maximum, this vertex? We don't know. So we'll have to use the other point, 4, -2, plugged into the equation to solve for the value of a, and that's what she does. So she ends up with a value of a equals -3, which you can then plug back into the original vertex form of the equation. Now, some people stop there because they didn't, or they forgot that, we're looking for an equation in this form, standard form. Okay, at this point, you're not done. I mean, you're done in the sense that, yeah, you have an equation, it is the right one, but it's not the form that it's asked for in the question. So the rest of the work here is really just, as she says, expanding, collecting like terms. Again, I'm not going to go through those details, and just writing it as, a quadratic, which is what she has here on the end. So your a value is -3, your b is 12, and your c is -2. Again, quite easy once you make that connection of expanding your vertex form equation into standard form. Let's look at this communication question by Julia Cochrane. The question asks, explain why a quadratic equation with a maximum above 3 passing through the point -2, 3 must have two roots. So why is that the case? Well, Julia, she illustrates the reasons why very succinctly. Okay, she doesn't equivocate. She doesn't put in words that are just filling in space in her explanation. She just says what's necessary and actually identifies that, you can actually determine the answer to this without using all the information given in the question itself. So let's see what she says. She says, if a quadratic equation has a max value, then that means that the parabola opens down. Obviously, if it's a maximum, then it opens down. So already she knows that it's going to go something like this. Great. Because the maximum value is above 0, okay, that means that it is above the x-axis. And how does she know it's above 0, by the way? Well, it's because it's above 3, right? So she marks the 3 here and puts the maximum above 3. And because it opens down, right, and the parabola goes on forever, as she correctly states, it will eventually hit the x-axis at 2 points. Technically, that was enough. Okay, she could have stopped there and not even used this idea or this information of the point -2, 3. But, she decides to go on and say it can be further proven because the vertex is higher than 3, therefore higher than the point on the parabola -2, 3. In order to reach this point, parabola must open down and continue to go on forever. So, she says because it's above the x-axis and it's opening down and it passes through the point -2, 3, which is over here, okay, it has to continue going down and intersect the x-axis at 2 points. So again, very succinct, doesn't use more words than necessary. This is kind of the stuff we're looking for generally in communication questions. Okay, sometimes the explanations are a bit verbose. Okay, you try to fill in with excess words. Pick your words wisely. Okay, you don't have to say a lot when you really want to say just a little bit. Let's move on to the next question. We're looking at this application question, courtesy of Chi. What's the information that's given here? So Mr. Kwan and his family visited the Amalfi Coast. While walking along the boardwalk in the picturesque town of Maori, his daughter noticed a pattern of stacked parabolic curves. So as you have in this picture over here. Let me get this black marker, okay? There we go. So we want to determine the equation of one of these curves, given that we know that it's 60 centimeters across and 35 centimeters high. So notice that the 35 and the 60, let me zoom in a bit, are drawn in. We're looking at one of these here. Okay, let me declutter this a little bit. So the question is, where's going to be your axes, your x and y axes? Is it going to be at the beginning, over here, or is it going to be in the middle? I mean, you can put x and y anywhere, okay? It really doesn't matter, but it's helpful to choose a spot that is easy to calculate. So Chi, in this question, he decided to put the xy axis, so the y axis, right here in the middle, okay? And the x-axis is going to be right over here. So that means we're going to go 30 back and 30 forward. Let me do that on a different, I think white shows up nicely on this. So 30, it's a bit too bold. So I got 30 here, negative that is, and positive 30 here, and 0 in the middle. And the height over here, the max, is 35. Let me try that again. So 35. Okay, and that's all in centimeters. Having identified the vertex, which is really just 0, 35, Chi then is able to sub that into his equation for vertex form. Okay, the h and the k is pretty easy, but it remains to determine what the a value is. And that's where you're going to have to use another point on the curve. So he decides to use, one of the endpoints, 30, 0, so 30 for x, 0 for y, plugs it in, does the work, ends up with an a value of -7 over 180. Plugs that back into the equation, and it gives him a formula for that parabola. Some students decided to turn that -7 over 180 into a decimal. That's fine, but if you can avoid it, use fractional notation. You can always round later if you need it on demand, but in this form it's probably best to leave like that. So the next part of this question asks to determine the coordinates of a tile which is 6 centimeters to the right of the axis of symmetry. Okay, round your answer to 1 decimal place. So 6 centimeters to the right, let's go back to our diagram here. I mean, if the 0 is the middle, that means 6 will be, 1, 2, 3, 4, somewhere over here. And to find the height, well, you just plug in the value of 6 into the equation that you just got from part A. That will give you the corresponding height. And that's exactly what she does. It's kind of pretty straightforward. It's only 2 marks. So by plugging the 6 in, squaring it, multiplying by -7 over 180, adding 35, well, that gives an approximate answer of 33.6. Again, you could have put that in a fraction, but decimal's fine here as well. Okay, so there are the application questions for, the first application question for the Unit 2 test. Let's take a look at the last one now. So in this last question, we're actually given, for a change, the equation, and we want to determine some information based on the question here. So we have an object launched at a certain speed, and from a certain height. So I'm going to draw here this 58.8 meter platform, and the object goes something like this. And why I draw it like that is because it is a parabola, so I have to draw it as such. And its height is given like that. Okay, so for a given time t, I have a certain height h, which depends on t. It's a function of t. And at some point it hits the ground over here. So first part asked to find the maximum height of the object, and Ethan decided to do probably the most natural thing, which is complete the square. So he takes the equation, which does have decimals, but that's life, and goes through the whole process of completing the square, factoring out the 4.9 from the first 2 terms, taking the b value, dividing it by 2 and squaring it, which he then adds and subtracts inside the brackets. Now before he continues, he takes out that last one and hits it with the -4.9, which becomes the positive 19.6 outside the bracket. Added to the 58.8 is positive 78.4. And what he's left inside with is a perfect square trinomial, which you can factor very easily. And he ends up with, his vertex form, where he can read off the value, the maximum height of 78.4, which is just the k value, or the y coordinate of the vertex. So that was, part A. Part B asked, when does the object fall below 45 meters? Now, there's no diagram here, so I'm going to draw one quickly. Maybe I'll take this here. Okay, this was kind of a sketch of what we had, going on at the beginning of this word problem. I'll put the y-axis there. The question's asking, at what point will it fall below 45? So remember that it starts at a height of 58.8. So this is 58.8. Just make it a bit smaller. It reaches a maximum height over here of 78.4. Okay, and that's after 4 seconds. So I'll put that over here. And then as it's coming down, it passes the original height that it was launched from. And I don't know, let's say around this point, let's say 45 meters. Okay, it will, you know, be 45 meters above the ground. So the question is, well, when does that happen? You know, at what time t is it 45 meters, okay, above the ground? And what Ethan did, let's go back to his work here, was, you know, pretty straightforward in the sense that he plugged in the value of 45 for the height. Okay, because at that time, whenever it is, we solve it, we will know it's 45 meters above the ground, and that pretty much answers the question that we're given. You know, when does it fall below 45? Well, exactly when t is a certain number and it equals 45. So how do you find that number? Well, once again, the beloved quadratic formula. He brings everything over to the right-hand side and identifies his a, b, and c value, as you can see in this step, plugs it into the equation, does all the work, which I will not go through, and ends up with two values, 4.6, negative 0.6, because the value is positive, and can only be positive in this case. 4.6 is the time at which it falls below 45 meters. So if you go back to our picture, the 4.6 is going to be about right over here, 4.6 seconds. And that's it. That is the Unit 2 test for you.